Okay, so let's get started. First of all, is everyone okay? Surviving the storm and everything? Okay, so sounds good. So here, so the test is on stuff that's already been discussed and kind of reviewed. We've gone through a problem set, homeworks, and we've discussed them. So this is kind of just like a little bonus, additional review kind of thing. So here, let me use my whole screen for this. Hold on a second here. Properties, transform. Okay, so the test it'll be during the normal class time on Wednesday, and if you want, you can start a little bit early, like 9:30 or even 9:20. If you come early, that's fine. As usual, make sure you plan to take the test in one sitting. If you think you need to take a break, I can give you part of the test and let you finish that. You can have a break and come back. So the test is fairly straightforward and simple. There are no double dot problems on this test. So you have, what happened to my hand here? One second. Okay. So there are no double dot problems, only undotted or a single dot problem. All of the problems will be from that first chapter, chapter 16 from the book. The theory will be both from lecture notes 1 and 2, that is chapters 16 and 17. So let's take a look so far. And before, did you guys get, can I see some more faces, by the way? Can you see can some of you turn on your videos? Okay. If you have a non-programming calculator that doesn't have any memory and so on, you can bring it. But otherwise, you can do what you did on the quiz. Just finish the calculation until the last step, and then so that all that remains is to plug the numbers into the calculator, and you can leave it in that form. Okay. What else? Okay, so that's kind of the general thing. Any questions about the general plan as far as the test is concerned? Okay. So let's go through the material very quickly. So this you kind of had on the quiz already. Let's see. Okay. So there can be trivia questions. So be able to state what's the law of conservation of electric charge. It just tells you that the total charge is constant. You can have a transfer of negative and positive going back and forth, but the total thing is constant. My face is getting hidden here. Let me move this aside a little bit.
Dr. Pincher,
Yeah, go ahead.
I have a question. So for this exam, it's all like the highlighted stuff on the notes.
So say that again.
So for this exam, like you know how you told for the quiz, like it can cover anything on like the theory. But for this exam, is it just like the highlighted stuff on the theory?
No, not necessarily. The highlighting is just to draw your attention to some of the important points.
Okay.
Those are kind of like bold, like using a bold font basically.
Okay.
But so I'm kind of giving you an overview of what all you need to know as far as the theory is concerned right now. So
Okay.
it's kind of just narrowing down the playing field basically. Okay. And so here, yeah, go ahead. Someone had a question. Okay. So you already had a question about charge and charging. So anything that's done on the quiz will usually not be repeated on a test, and vice versa. And similarly, a problem that appeared on the quiz, it will not reappear on the test. So we are already done with some of this earlier stuff. So starting with this point over here, know what the law of conservation of electric charge is. Then why do materials charge in the first place? Because you have differences in electron affinity. Then what is Coulomb's law? You can have a trivia question, just state Coulomb's law. But of course, you may also have to use it for problems. Okay, then know the units of everything. So for electric charge, the unit is a coulomb, capital C. Then what else you have here? So I've scratched out some stuff that you don't need. So this is just a problem that we did. Let's see, electric field. Know what the electric field is. The electric field at any point in space tells you that if you were to put a charge there, the charge will feel a force. How much force? That force is equal to the electric field times the charge. So know the basic defining equation of electric field. So here it is. So this thing in yellow, E is equal to F over Q, and F is equal to E times Q. This is a vector equation. So if you are given the x and y components of one, you can find the x and y components of the other one. So that's what this thing is. So these are things that you should know. Then the unit for electric field, it's a Newton per Coulomb or a volt per meter. They're basically the same. Then so these are again more trivia questions and like a conceptual question. Know what happens inside a conductor. So if you have a metal conductor, let's see, like this remote over here, if this whole thing is made out of metal, then there's certain facts about this. There is no electric field, no static electric field inside a metal, because if you had an electric field, the charge carriers can move, therefore they will move, and the pluses and minuses will rearrange to make sure there's no electric field inside the bulk of any conductor. So the electric field is zero. Secondly, we learned in the next chapter, the electric field is the gradient of the potential. Remember those contours and all of that? So the steeper the change in the potential, you have an electric field. If you don't have an electric field inside, it means the potential is constant. It's not zero, it's just constant. And then the third thing about conductors is that there is no static charge inside a conductor for the same reasons as stated above. So since if you had a charge inside, you have an electric field, just from Gauss's law. A charge produces electric field lines, which produces flux. So since you can't have an electric field, you can have flux. That means you cannot have a charge inside. So the charge inside any conductor, static charge, is zero, basically. So these are some important facts to remember about conductors. Then moving on.
Can you repeat
Yeah.
the 3 points again?
So they cannot. The charge inside a conductor is zero, right? And if the charge is zero, the electric field is zero, because Gauss's law connects the electric field to the charge. So does Coulomb's law. So if the charge is zero, the electric field is zero. If the electric field is zero, the potential is constant. Okay, so the potential is not zero, it's just constant. Because if you have a change in the potential, that gives an electric field, which is something that we discuss in the next chapter. Remember those contours? If you have a flat land, like anything that's basically flat, and you put an object on it, it's not going to roll. So that doesn't mean that the height is zero. It just means the height is constant. So a constant potential gives you a zero electric field. So those things are connected. Okay, any other questions about this point?
I have a question.
Yeah, go ahead.
So, because there's no charge or electric field on the inside, does that mean that the charge jumps to the surface of the conductor?
Correct. So if you that's why the Van de Graaff, inside the Van de Graaff, I mentioned for research purposes long back, we had this big thing the size of the physics building. You could go inside that with 8 million volts on the surface. Nothing happened to you. Where all the charge sits on the surface. It sits on the outside. Hence the safety of being in a car during a thunderstorm. The charge and all the bad stuff, it goes through the car outside. You're sitting inside and you're safe. So the charge sits on the surface. Excellent point. Yeah.
There were a few questions, like in the textbook that were talking about the Gaussian surface. Is that like the inside of the conductor?
Correct, correct. So you will not have any complicated problems involving Gauss's law.
Okay,
Yeah,
thank you.
so don't worry about any problems involving Gauss's law. No problems involving. So we will after going through the theory, I'll discuss like which are what type of problems you kind of have to look out for, and we can even do some if you want. Okay. And so where were we? Okay. Yeah. So that was this business here. Then just have a general sense that anytime you have charges, you have these things flying out. It's like a fan blowing a breeze, and a positive charge puts out, the lines go away from a positive charge, they go towards a negative charge. Okay, and these are some field patterns. Let's see. Okay, and then know what electric flux is, and be able to do simple problems on electric flux. They're trivial. Look at that. It's just E dot A. So the dot is like an abbreviation for the cosine theta. So it just tells you that to find the flux is a scalar, by the way. The left hand side is a scalar. It has no direction. The direction got eaten up by these two vectors multiplied together. So you put the electric field, you put the A, and you put the cosine of the theta between them. Remember that the theta is the angle to the normal. So this is the surface. This is not. This is the normal to the surface. So the electric field is going this way. So here is the electric field, and there is the normal. The angle is between these two things. It's between the pencil and this purple pen over here. Don't take the angle with the surface itself. It's the normal of the surface, and that's what that is. Okay, any questions? Okay, this part clear? Okay, very straightforward business. Okay. And then, yeah, go ahead. Yeah.
Anytime that they give you theta and they say this is theta of the normal, is that the theta that you would use and you wouldn't have to solve for it?
Correct. If they tell you the angle of the electric field is, let's say 45 degrees with the 40 degrees with the normal to the surface, then that 45 degrees is what's going to go directly in there, basically.
Okay, thank you.
Sure. Okay, nobody's waiting in the waiting room. Okay. Okay, so let's see, we have this. So I've scratched out things that you don't have to worry about. Okay, then electric dipoles. You have the formula for the torque on a dipole. So if the dipole, you take the negative charge and you take the positive charge and you draw an arrow from the negative to the positive. That's the vector representing the dipole. And then if you have an electric field like this, then the torque is given by, this is the angle between those two vectors, by the way. So you take the dipole moment, the P, times the electric field times sine of theta. This is not a dot product, it's a cross product. You have sine theta instead of the cosine theta. So here on the slide, where's my cursor? There it is. Okay. You see, this is minus Q, this is a plus Q, there's the electric field. You take the angle between these, and sine of theta times the P times the E, that's the torque. So here it is, what is it? There we go. Yeah, you see the torque? So that's equal to PE sine theta. And what is P? P is the dipole moment. So the P is, you take the charge Q and you multiply that by the distance between them. So here is P equals QD. Are you guys able to see my little cursor? It's like a small hand. I wish the cursor were bigger, but anyway. Yeah, so that's what the dipole moment is. So if you're given a charge or whatever, you multiply the charge, let's say 5 coulombs, and let's say the distance is 4 meters. 5 coulombs times 4 meters is 20 a coulomb meter. That 20 is the dipole moment, P. P, there it is. So this P over here. And so that's P. And so to calculate the torque, this is the equation. The other equation that comes about with dipoles is the flip energy. So if you have a dipole pointing this way and it's aligned with the electric field, it tries to point along the electric field. If you suddenly change the electric field, this will flip. That's what happens in a microwave oven. The energy to flip it from one side to the other by 180 degrees, that's the U flip energy over here. And so there it is. So that U flip is 2 times P times E. So remember this important formula. That's the energy required to flip the dipole from one side to the other side, basically. And that's 2 times the P times the E. Okay, any questions? Okay. So on we go. Here's an example of a dipole. And then, okay, so we just summarized everything. No need to look at the summary. So here, KQ. So in this chapter, we introduce the idea of, so there will be no problems, no textbook problems from the chapter, only the theory along the lines of what we discussed for the previous chapter. Okay, so the force is K Q1 Q2 over R, but that's the Coulomb's law. But the potential energy, there is one R missing. It's K Q1 Q2 over R, or big Q small q over R. So there is no R squared, just a single R. And that comes because when you do the work, you multiply the force times the displacement, and one of the R's disappears, basically. And then remember this concept of electric potential. So whatever is the potential energy, that divided by the charge that you're moving to that point, that is the potential. So it's like raising something through a height. Let's say this is sea level, mgh, the gravitational potential energy is 0. If you lift this baby up like that, the work that you do is mgh. That's the potential energy. But if you remove that m, just the gh, that would be like the potential. So whatever mass you have, you multiply by gh, that gives you the potential energy. So the connection between potential and potential energy is what I just mentioned right now. And then let's see what else we have here. Okay. So yeah. So and then the gradient in this comes again later on when we get to the contour diagram. But the gradient in the potential is the electric field. So if the potential is changing from here to here by a certain amount, that divided by the displacement, that's the electric field. This becomes clearer when we get to the diagram. And so don't worry about the examples right now. Okay. So here are those contour diagrams. This is a 3D profile. It shows you a hill. As you walk up, you have this equal height contour. As long as you're on a certain dashed line over here, you're at a certain height. So the mgh, that is constant. So the potential energy and therefore the potential stays constant. This is a flat contour map. You kind of flatten this diagram. It looks like this, same idea. The point is where the potential is changing rapidly, you have a steeper slope, you'll have more force. So the gradient here, when the contours are close together, the potential energy changes in small steps very quickly. That's a steeper slope. So this is for height and for gravity and for regular hills that you might climb on. The same applies to electric potential. So there it's three-dimensional, but you can kind of take a slice like you do with an onion and just look at the same contours in 2D. And then you have the same idea over here. Near a positive charge, the potential energy is higher, so the potential is higher. So if you brought a 1 coulomb to any location, the potential energy and the potential, they're the same. And so you have equipotential contours over here, where the potential is constant, just like the hill. And then the electric field lines are perpendicular to these contours. And this is like a 3D profile of the same thing, like you had with the hill earlier. Okay, any questions? And then this is for a dipole, positive and negative. Okay. And this was kind of, so here near a sharp point, so remember what happens near a sharp point? the electric potential falls off more rapidly. So that's like that steep side of that hill where the slope is changing rapidly, you have more force. In this case, you have more electric force, more electric field. So near the sharp point, the potentials are the contours are close together, 400, 300, 200 volts, and so on. So as a result, if you were to put a charge there, it feels a bigger force, and consequently you have a higher electric field. And this was a little calculation that connects the dots together basically. If you moved a charge Q from 200 to 300 volts, you would multiply the difference of 100 volts times the charge. That would be the potential energy. Any questions?
Can you repeat that again?
Yeah. So did you get the part about where the contours being close together represent a higher electric field?
Yes.
Okay.
Let me just write that down.
Yeah. So the other thing was like a application of that. So if you move a charge, it's shown over here, but this is a bigger magnified view of the same thing. If you were to move the charge from the purple line to the green line, shown bigger over here, move the charge from 200 volts to 300 volts, it's like climbing up a hill. So you move the charge from 200 volts to 300 volts. So the work required when you do this thing over here, it's going to be the charge times the difference in potential. Okay, so that's what the work, here it is also, you can see that. So the charge times the difference in potential, that's that work done. And so this gives you the connection that the electric field is the gradient of the potential, and the electric force is the gradient of the potential energy. Is that okay?
Yes.
Okay. So on we go. Okay. And this business of having high electric fields near a sharp point is why lightning is more likely to strike sharp point. So they purposely have these sharp pointed metal things on top of tall buildings and a thick conductor going to the ground, so that electricity doesn't go inside the building and cause damage and so on. Okay. Then remember this stuff over here, the electric potential in the context of charge conductor. So as we discussed earlier, the charge sits on the outside, and then we also discussed at some point that a sphere of charge has the same electric field and same everything as a point charge at the center. So it behaves the same. We actually did a proof of this using Gauss's law a long time ago. You don't have to worry about that proof. But the point is, when you have a spherical conductor and you put charge on it, it sits on the outside. Now the potential, we already had that formula from the previous sheets, previous pages. The potential is KQ over R. So now, so based on this, you can calculate the capacitance. So the capacitance is the idea that the more charge you can store without increasing the potential, that's a bigger capacitance. So that's the same as filling water in a container. If you put a certain amount of water in here, say 2 ounces, it's going to rise to a certain height. If you have a wider base, a bigger one, then it will not rise as much. Less work has to be done to add water to something that's more flat. There's something with a bigger base, bigger real estate basically. So the same way that a capacitance with a tank with bigger base can hold more water, the same potential, you have the tank capacity, same idea works over here. If you have a bigger sphere, then in that case you can spread more charge because they're spread out over a bigger surface. It's kind of less concentrated, more dilute. You raise the potential energy less, you raise the potential less. So as a result, a bigger sphere will have bigger capacitance. This is the electrical capacitance. The symbol for capacitance is a capital C. This is the definition of capacitance. So remember 2 different things. This is the definition, Q over V. But what's the value for a spherical capacitor? So this is a small little derivation, be able to explain and do this. The charge, the capacitance of a sphere, the definition is Q over V, where V is the potential, not the volume. So that's equal to q over, earlier we found that up here, there it is, v is equal to kq over r. So the potential for a point charge or a sphere is kq over r. So if you put for this v the kq over r over here, a whole bunch of things, as you can see, get cancelled out. You're left with r over k. This is a formula. This is the formula of a spherical capacitor. So be able to derive this. You have like 2-3 steps basically. So, so that's the formula for a spherical capacitor. And then we discussed parallel plate capacitors, but we won't do anything with that over here. We'll save that for another time basically. Okay, and then the other thing we discussed, let's see, okay, so you won't have any numerical examples here. Let's see. Oh yeah, the one other thing we discussed, where is it in the notes? Is the following. We discussed insulators. We did the demonstration with the Van de Graaff accelerator. So make sure you understand all of those demos. I'll put those videos on the line also online as well. But we discussed that as you increase the potential and the electric field, in the first chapter we discussed a distinction between insulators and conductors, but every insulator has its match. If you increase the electric field more and more, you'll rip apart the electrons away from the proton. They will move, even if they don't move at a small electric field, they will move at big electric field. And that's the concept of electric field breakdown. You remember this? So if you have something that's an insulator, the electrons don't move, but if you keep increasing the electric field, those negative electrons are pulled one way, the positives are pushed the other way, they will break free and they will start to move. So that's what happens in the case of lightning. So when you keep charging this thing more and more, at some point the electric field becomes unbearable, and the air that used to be an insulator is no more an insulator. It gets ionized by brute force, and then the spark jumps across. So every insulator breaks down beyond a certain electric field. And this is the concept of the breakdown electric field of an insulator. Okay, any questions? Okay, so the test will have 3 theory questions and 3 problems, and it should not take you more than 2 or 3 minutes for each of them. So it's very straightforward stuff, and so really the test is doable within in less than 20 minutes, but you'll have more time. So that's kind of the plan.
I have a question. So
Yeah.
like, is it like the 3 theory questions? Is it going to be like having like subparts to it, like A, B, C? Like, how much is a whole exam worth out of? Is it like out of 24 points, like 20 points, 25 points?
Right. So the theory questions, I haven't finalized the test yet. I'm thinking something like 3 points for each of the 3 theory questions, something like that. The points gonna give you an indication of how long you should spend. So it should not be taking more than 3 minutes. It shouldn't take more than 1 or 2 minutes really. But it should absolutely fit your reply. If you know what it is, it should fit easily comfortably within 3 minutes. And the problems, as usual, will be like 4 points or something like that. Same rule kind of applies there. It should not take you more than 3 minutes to do each of those problems. Especially if you are not punching in the final numbers. You kind of to take an example. Let's look at an example here. Okay, so here, looking at this example, you have a proton, and then you have they give you the mass and the charge of the proton. And there is a mass and there's the charge. Then this is accelerated from rest through 300 volts. Okay, so it went up from 100 volts, from 400 volts to 100 volts, or 500 volts to 200 volts. Anyway, the difference in potential is 300 volt. So that 300 times the charge, that 1.6 that they gave you, that's the change in the potential energy. That's the increase in the kinetic energy. Shall I switch to my? Are we done with this document here? Can I switch to paper and pencil? Okay, yeah. I can actually bring this up if I need to. Anyway. Mm. Okay. Okay. So, oh, and I lost the question. What is the question? Proton. Okay. So this is 17.9. To the 27. And so you have except for potential of 300 volt. Okay. Okay. So here's the problem. It's like water flowing downhill as it goes to lower and lower height. It's losing potential energy. It tries to gain kinetic energy, aside from the friction. So the same business over here. The electric field is in this direction. Okay. So the electric field, the direction of the force is always downhill as far as the potential energy is concerned. So you have higher potentials over here, and they're getting less and less. So it's like water flowing downhill. Now it falls through, just like if water falls through a greater height, it picks up more kinetic energy. It loses more potential energy. So in this case, you have the delta K, kinetic energy. This is equal to minus delta U. And in terms of magnitudes, they are equal. The changes are equal. So this is equal to 1/2 mv squared. That's the kinetic energy. And this is equal to the change in energy is equal to the charge times the change in V. And so as a result, let's see. So we are trying to find V. This is the question over here. So therefore, V will equal to Q delta V over M, square root. And this delta V is 300. The Q is 1.67, no, it's 1.6, 10 to the minus 19. Okay, and what else? The mass is 1.67, 10 to the minus 27. Okay, so yeah, so Joshua, so this kind of a question, and you would leave it like this. You would put those numbers inside instead of these long equal signs that I have. Just go one more step and put those numbers inside. But so it's not a very complicated problem. You can basically leave it up to this point. You won't have. Yeah, go ahead.
Yeah, sorry. I was just like, these are easy, but how would it do with like decide like a cosine or sine? Like would we just like if it has like multiple steps for like the math part, like it's like 2 or 3 steps, and we have to find like one step, find the math, like find one of the values, and then put it
You
back into like straight
you just leave it so first thing is, as far as possible, even otherwise, calculators or not, try to solve things symbolically. Don't deal with numbers. Solve the things symbolically as far as you can anyway. But if you're used to putting numbers, you can put numbers over here. So this is the formula at this point. So you can put in intermediate numbers if you need to. Does it make sense? So let's say this is k. So here I could do it this way. So this will equal the change in the change in kinetic energy. That's equal to 1.67. What do I have here? 1.6 10 to the minus 19 times 300 volts. So if you have an intermediate thing, you will leave it like this, Yoshida.
Yes.
You would like this, and then bring that to the next step, and so on and so forth. So if you have a cosine of 30 degrees somewhere along the way, write down cosine of 30 degrees, in that form without a number, cosine of 30, and then just let that percolate into the next step.
Yes. Okay.
This is to avoid the hassle of the calculator's business, because otherwise those graphing calculators and some of these more sophisticated ones, they have huge memories. You can store your entire life's history on one of those calculators, basically. So then the simpler scientific calculators, I don't know if you have time to buy or not. So I ordered a bunch of them for you guys, by the way. But now, because of the weather, Amazon told me that they will not be delivered before Wednesday.
Okay.
Yeah,
So I don't have a simple calculator, so I might be just doing.
yeah. If you don't, if you have a simple calculator, if it helps you, you can you can calculate intermediate numbers if you want. If you don't have a calculator, just percolate the numbers until the end. What I would do and what I recommend is to actually do it symbolically, as far take it symbolically as far as you can take it. Then put the numbers at the very end. You just have less computation to do. If you compute along the way, later on you may realize that cosine theta cancelled another cosine theta. So there was no reason to calculate it in the first place. You see what I'm saying? So it's good to keep it symbolic. Then the thinking becomes more clear. You can see what the logic and what the physics is. As soon as you have a number is kind of more abstract. But we'll see. If by some miracle those calculators arrive by Wednesday, I will bring them. But to make the whole process as painless as possible, they were like $5-6. I thought I'll just go ahead and buy a bunch of them, so I did. Okay, any other questions?
I have a question.
Yeah.
The math problem that you just showed us is like a chapter 17.9. Are we gonna have ones like this on our exam?
No. So you won't. I just went up in those notes and looked at the first problem I could find. This was just to give an idea that if you don't have a simple calculator and non-programmable and all of that, you can just kind of leave it in this form.
Okay, that makes sense.
Yeah, that's the reason I did this. I just did the first example that my cursor hit as I went up the note. You will not have problems from 17.9. But the concepts that we talked about, the in reverse order, what was it, like the breakdown electric field, how an insulator turns into a conductor, under a sufficient brute force electric field, it tears it apart. And then, let's see, let me go back to my note.
I have a question.
Yeah.
So for the quiz, it was only from 16.2 to 16.5. So is for the exam, is it all of it, or just from like 16.2 to 16.5?
Say that again. Let me maybe bring up those problems.
You told for like the quiz before we took, like, you sent an email out, and for the quiz, it was not like the math problems were just from like a certain section. Like it wasn't like all.
Oh! I see what you're asking. Yeah. That's a good. I'm glad you asked that. So in terms of what section, let me look. Let me bring up that those physics problems, that PDF. Where is it? Okay. Okay, yeah, good point. So it'll kind of narrow down the playing field, so to speak. Where is it? Excellent question. Mm, where would it, okay, there we go. Homework and related. Oh, yeah. 202 problems all. Here we go. Okay, yeah, I'm glad you asked this. Okay. So now I have to go to that sheet here. Video calculator, full PDF. Let's see what happens if I do this. Where is it? So here I change the document. What's this thing called? Problems. P202. Yeah, and I should add that to the review that I posted also. So the document I went through, the one we are looking at right now, that's posted on the website. And I'll put a revised version of that with the information we're about to discuss, like which sections do you need to focus on as far as problems are concerned. Let me bring up that thing. Here we go. Why do I not see it? Oh, here. It's being covered by the other one. Okay. So now let's look over here. So the first section is Coulomb's law. Again, don't worry about the double dot problems. Oh, are you able to see this?
We can see it.
Yeah, okay. So yeah, don't worry about the 16.14 and so on, double dot. The 16 point on your quiz, did you not have a question involving superposition of electric fields? I think you did. Okay, but 16.3 is a possibility. Then 16.4. 16.4. What is this? Superposition electric field. 16.4. Skip 16.5. You had a question about that on the quiz. So generally something that's come on the quiz will not be repeated on the test. So skip 16.5. So from this chapter, what did I just say? Section 1, 3. Let me write this down. Okay. So problems from, you can't see the sheet I'm writing on, but I'll scan it later. So problems from sections 16.1, 16.3. There is no 16.2 somehow. 16.
Is there 16.2 or just 16.1, 16.3, and 16.4?
Yes, I'm looking at the section. Where's my hand? Here we go. You see here, there's like a section 16.2. These are the numbers that I'm referring to.
Okay.
So this section 16.2, and then 16.3. This one over here. Okay. Yeah. In fact, that's really the same. Okay. 16. I might even. I will look at this a little bit later. We might even skip 16.3. 16.4 for sure. Then 16.4. So skip 16.5. You had that on the test. Then skip. Okay. What is this? Electric flux and Gauss's law. Okay. So Gauss's law, 16 points, this one here, 16.6, 16.7. What is 7? Okay, 16.6, 16.6, 16.7. Okay. So 16.7, Holy Spirit. Not beyond problem 16, let's say large insulating sheet. So no direct application of Gauss's law. So skip the problems beyond 16.47. So skip problems 16.47 and beyond. Okay, so that section, but really the first looks like 5-6 problems or something. All right, then we come to electric dipole. Where is that? Okay, there we go. So electric dipole, so that's 16.8, 16.8. So you have 16, the section 16.8, electric dipole. So it could be like don't focus on the double dot. And for practice, there is some this business of addition problems also. If you need, you can practice look at these as well. But those are the sections. In the addition problems case, all the sections are mixed up together. But in the earlier ones, they're kind of segregated by section. But those are the sections you need to know. And the problems under the section, they sort of exemplify. Let me get rid of this so you can see me. Okay. So I wrote it down over here. So, so the addition problems too, but this kind of 16 point, there could be a problem from the addition problem, but this kind of gives an idea of what type of problems to skip, to not worry about, basically. Okay, so it's a straightforward. Yeah, go ahead. Someone was saying something.
Oh yes, I was making sure on the exam our questions are going to be from the textbook.
Yeah, yeah. This document that we just looked at, it says P202 problems dash all PDF. So every problem on the exam, all exams and quizzes will be from this document.
Okay.
So in principle, there cannot be an unseen problem. But of course, there are dozens of problems. There's no need to do many problems. You do a few. You want to do problem solving with quality. Do a few with complete understanding and working out everything with setting up the theory and all that, and that's all you need. You don't have to practice numerous problems, basically. Understand the principle. But these are ones I just gave you, kind of highlight, will sort of focus your attention, so to speak. Okay, is this clear? Okay, and I'm gonna I have recorded this and I'll post it. I may try to add caption. The captions and rendering process, that adds 2 hours to the workflow, basically. So I'll just post it as it is. There won't be caption. YouTube can give you caption if you click on caption. They may not be as accurate, but it's something if you need caption. But I'll just upload this as it is. That uploading, this is a 1 hour video. Oh my God, it'll be like, I don't know when it'll be done. Late in the evening tonight, before tomorrow morning for sure. It's going to be up there. It looks like it takes 8 hours or more to upload. I looked into other internets, by the way. I was going to purchase fiber and some other internet. Nothing is available in our area. This is the fastest I can get, Spectrum. I was willing to spend money and do whatever it took. But this is the best in our area. Fiber hasn't reached our neighborhood for whatever reason. So it's either this or, like Wi-Fi or cell phone or something. So that we are kind of stuck. But so
Also,
yeah.
Do we have a Google Meet tomorrow to go like over any like math problems, or it's just this is a review?
The problems are fairly easy, as I
Oh,
mentioned. So if you want, we can. Uh, would you like to have a short meeting tomorrow? Okay, then we need to vote on a time. Can you, let's see, tomorrow is Tuesday. How is 6 o'clock? You can, you can, you can turn on your mic at any time and speak if you want. Say 6 is okay? Anyone want slightly earlier, later? Okay. So far, I'm only saying a thumbs up, upward pointing thumbs. Okay. Okay. So, sounds good. Good. Okay. Yeah. Any nays? Thumbs down. You can. Okay. So 6 o'clock it is. So the test is simple. Life is easy and simple. Don't make it more complicated. Make sure you know the theory. As I mentioned, the theory questions are simple and direct. 2 minutes. There are 3 points. So 3 minutes is the absolute maximum you should take for each theory question. The problems are rated at probably they'll be worth 4 points something. It makes it easier for grading. But again, it should not take more than 2 or 3 minutes. So if you're prepared and you don't go on a sort of a hunting expedition during the test and try to learn the stuff for the first time, you should be done in 20 minutes, 30 minutes tops. Okay, that's the plan. And so I'll print out the test and bring everything you need. If by some miracle those calculators arrive, you'll get to play with a shiny new, brand new calculator. We'll see. Okay. All right. Any other questions or comments? Anything?
I have a kind of random question
Sure.
about Coulomb's law.
Uh-huh.
Um, I was doing some of the practice problems and noticed there was like a little bit of a difference. Do we always use the absolute value of the Q or like the charge that is given to us, or do we keep the negative and positive signs?
Okay. So Coulomb's law, the spirit is to give you just the magnitude.
Okay.
So if you have a charge Q1 and Q2 like this, then separated by a distance r, then this Coulomb's law, this F, you can keep the sign or not, but it does not give you a direction. If you were to include the signs, if you kept both positive or both negative, you'll have a positive force. A positive force is viewed as a repulsive force. If you kept the plus and this is a minus. If you kept the plus and minus signs, you'll get a negative force. A negative force is attractive. It doesn't really add any information. Well, it doesn't tell you the direction. You still have to look at these are the two charges, so the force is in this direction. It doesn't give you the vector direction. So the safest thing is that view this as just k, q1, q2 over r squared. You can just put in the numbers there, and that gives you the magnitude. Even if you kept the signs, the best it does is tell you whether attractive or repulsive. How useful is that? It doesn't give you the direction anyway. It doesn't give you the vector direction. So that is to put in by hand. So the Coulomb's law gives you just the magnitude. Then the forces along the line joining the charges. Those charges could be at a 45-degree angle. So this useless equation doesn't tell you that. But then you look at where the line is and measure the angle to the x-axis. That's going to be your angle. And then and the force is attractive and so on. So I would just go with the magnitudes basically.
Okay, thank you.
You can apply the logic on top of that. Okay, any other questions? Okay. So tomorrow we'll meet at 6. If you have any remaining theory questions, we can deal with them at that time as well. Do some problems. If you're stuck on some of these problems, we can look at them tomorrow. The problems are simple and straightforward. So if you're stuck on a problem that seems horrendously complicated, then I'll just tell you that that's more than what you could be asked about on the test, and we won't even have to worry about it. But just for the sense of adventure and so on, if you want to try some more complicated problem in a double dot or not, to do it for your own entertainment. But I'll let you know then whether that's a type of problem that you even need to worry about. But if the answer is yes, you need to worry about, then we'll discuss it and do it. Okay. All right, everybody. Okay. So you can stay on if you want to talk about anything else, but otherwise, let me go ahead and stop the recording in any case.